earlier we saw the binary log-Sobolev inequality. Log-Sobolev inequality, which said the following: let x be distributed uniformly over the Boolean hypercube, the sign version of it, and we looked at this function f from so on 1n to r, let's say non-negative function, or let's say positive function, then actually just r, and then what we showed was that the entropy of f square is less than equal to 2 times E of f, which was the sort of which was what we call the Herbst variance estimate for f. Okay, this was the binary log-Sobolev inequality we saw, and this implies we saw that this gives the Gaussian log-Sobolev inequality, which again now it looked at x being Gaussian with mean 0 and identity variance, and again f was this function from r into r. So this inequality said that the entropy of f square is less than equal to expected value of gradient of f square times that. And so these two inequalities we had derived earlier, and what we claimed was that once you have these inequalities, you can establish sub-Gaussian concentration bounds. So using these two inequalities, we were able to establish sub-Gaussian concentration bounds for in this case, let's say Lipschitz function of Gaussian random variables, and here for functions for which this the Herbst variance estimate was bounded. That's what we were able to do. Our goal now is to extend these bounds and subsequently the concentration bounds of similar form to general random variables. That's what we want to do. So in the first part of this lecture, we'll derive a modified log-Sobolev inequality which extends both of them to general random variables. So here is our modified log-Sobolev inequality. So now once again we have this random variables x1 to xn that are independent, and we have a function f from these n random variables. We will just write it as f of x1 to xn. This is a non-negative function, and we define another random variable zi, which is some function, let's say fi of x1 to xi minus 1, xi plus 1 to xn. Can be any function. And the log-Sobolev inequality, the modified log-Sobolev inequality that we are after, says that the entropy of e to the power lambda f, actually this e to the power lambda f is there, so we don't really need this to be non-negative. So entropy of e to the power lambda f is less than equal to expected value of e to the power lambda f, entropy of lambda z is less than equal to expected value of e to the power lambda z phi of minus lambda to z minus zi summation I equal to 1 to n. Okay, so this is the modified log-Sobolev inequality. This looks a bit like the log-Sobolev inequality, but we are applying it to this function e to the power lambda z. And in fact, if you remember the proofs of concentration bound from both these binary and Gaussian log-Sobolev inequality, we did apply them to the function f that was given by e to the power lambda z. So in that sense, this inequality directly gets us there and hopefully will serve that purpose. Okay, so that's the main inequality we'll show. Where I never defined this function phi, where phi of x is equal to e to the power x minus 1. Okay, so let's prove this inequality. Lambda non-negative, lambda greater than 0 actually. So the proof relies on the formula the variational formula for entropy that we saw in the previous class. So recall that the entropy of a non-negative random variable y can be expressed as soup over, say, u that is greater than 0, expected value of y log y by u minus y minus u. So this is the formula we saw in the last class. Also this tensorization formula for entropy, it said that entropy of a random variable y, which is a function of x1 to xn, is less than equal to expected entropy all but the ith random variable of y. Okay, so we apply this formula to this conditional entropy. We have, this is a general recipe for proof of all the log-Sobolev inequality, where we reduce the bound for n-dimensional case to the bound for one-dimension case. So we're doing the same thing here. We'll derive a bound for entropy I here. So in this entropy, everything but the ith random variable xi is fixed. So this expectation is over just the random variable xi. Okay, and this is equal to, or let's say this is inf, not soup. It is important. Right, so this guy is less than or equal to, I can choose any u here, I'll choose a particular u. This expectation is with respect to everything but with respect to the ith random variable, so everything else is fixed. And I will fix u to some function yi of all the other random variables. Okay, where yi is some appropriate function gi of all the other random variables. Okay, so we have this formula. Now, so this is true for any random variable y. So this implies entropy of y is less than equal to summation I equal to 1 to n expected value of y log y, because this is expected value of this expected value, so that becomes expected value of y log y minus log of yi minus y minus y. Okay, so this is true for all y. So considering y equals to e to the power lambda z, so this y is a function of x1 to xn, so this z is also a function of x, and this z is also a function of x1 to xn, so this is allowed, and yi is e to the power lambda z. We can do that. Okay, so setting this to values, setting we get, so we just substitute these two values. Entropy of e to the power lambda z is less than equal to summation I equal to 1 to n expected value of y, so e to the power lambda z into log y, that's this lambda comes out, so that's lambda z minus zi minus it's better to keep this lambda inside, lambda this minus e to the power lambda z minus e to the power lambda zi. Okay, just substitution. So this is exactly equal to summation I equal to 1 to n expected value. We take e to the power lambda z outside, and what we get inside is lambda z minus zi minus 1 plus e to the power lambda zi minus z. Okay, and so if you look at this function here, this is e to the power minus lambda z minus zi minus lambda z minus zi minus 1, so which is just phi of minus lambda z minus zi. Okay, the function we were looking for. Okay, so we have shown that this thing is nothing but summation I equal to 1 to n expected value of e to the power lambda z phi of minus lambda z minus zi. So this general bound, that's what we were after, is called this one here. So this is called the modified log-Sobolev inequality, and this function phi, it has some approximation properties which we will use to obtain concentration bounds. Okay, so this is the modified log-Sobolev inequality, and in proving this we again use tensorization property, and then we proved an inequality, an elementary inequality, this so-called, let's say, a sort of elementary inequality here that we applied. This is that variational formula for entropy that we had seen earlier. Okay, so now that we have our modified log-Sobolev inequality, we move to the second part of the lecture where we use it to derive a concentration bound. Okay, so that's the second part of the lecture. So generalization of multi-Herbst bound. Okay. Okay. Right. So before we proceed, we note a property of this function phi that will be used in this bound. But maybe we state the bound first. So suppose f is a function from, let's say, it not be IID, so like I'll say x1 to xn to r and x1 to xn are independent. Okay, and then let's say this, so we denote this random value of the function by z, and this zi can be any function of our choice. So we choose this guy to be inf over xi f of x1 to xi minus 1 xi plus 1 to xn. Okay, that's what this guy is. So suppose we assume, suppose that this minus this zi square summation I equal to 1 to n. So this is non-negative. Okay. Suppose this is less than equal to v. So as I have remarked earlier, this is sort of a generalization of the bounded difference property. Earlier in the binary log-Sobolev part and the Gaussian part, we were taking zi prime, which was an independent copy, where we had replaced xi with its independent copy, and now we have taken inf over all xi. This is slightly different form for from what we saw for the binary case and the Gaussian case, but that's what we assume. It's still a condition which relaxes. So this is a relaxation of the bounded difference property. Because if you go by bounded difference property, you need a bound for individual terms. So you need sort of a bound on L infinity norm of this vector, but now you need a bound only on the L2 norm. So, suppose this is true, then the probability that z exceeds its expected value by t is exponentially small, and this variance factor v is the same as this variance factor v. Okay, so this is sub-Gaussian concentration bound, the one we have been after throughout our treatment of entropy method. So this can be one concrete attainment of a concrete inequality which we obtained using the entropy method. We were able to generalize McDiarmid to just this assumption. Instead of requiring assumption on each and every term, now we only have an assumption on a total difference, and we can establish McDiarmid's inequality. So how do we show this? Okay, so this is the main thing. Proof. So we start with this modified log-Sobolev inequality. Log expected value of e to the power, that's correct, lambda c z is less than equal to summation I equal to 1 to n expected value e to the power lambda z phi minus lambda z minus zi. This holds because zi here is a function of all but the ith coordinate. Okay, so if you fix x1 to xi minus 1 and xi plus 1 to xn, you can view the zi as a function of these guys. Okay, so this is true. Now note that the function gt defined as phi of minus t for t greater than equal to 0 satisfies. So let's see. So this gt is e to the power minus t plus t minus 1. So g of 0 is 1 minus 1 and 0, so 0. G prime of t is minus e to the power minus t plus 1. So g prime of 0 is also 0, and the second derivative is e to the power minus t. Okay, so that's prime of t, and therefore if you want, this is less than equal to. So let's just keep it this way. So therefore, GT is less than equal to this guy is less than equal to 1 by is less than equal to 1. So GT is less than equal to t square by 2. So right, so its derivative is always less than equal to t, and then this implies GT is less than equal to t square by 2. Okay, that's the proof. Okay. So we have this bound, and so this is our first observation. This is the modified log-Sobolev inequality. This is some elementary bound for this function. Earlier it was not clear why do we have this function, but now we have this nice property for the phi function. So combining 1 and 2, we get that the log expected value of e to the power lambda z is less than equal to summation I equal to 1 to n expected value e to the power lambda z. Now we substitute this bound lambda square by 2 into z minus zi square. Very nice. So this expected value e to the power lambda z comes out, and we have lambda square by 2 summation I equal to 1 to n z minus zi square. The quantity that we have assumed is bounded by v. Okay, and so therefore this guy here is less than equal to lambda square v by 2 to expected value e to the power lambda z. Alright, so now we have a familiar this is the bound for the entropy of e to the power lambda z. That's the bound that we derived, and so this is also the entropy of e to the power lambda z. That's what we need for entropy method. We need a bound for the entropy of e to the power lambda z. Okay, so what we have is that the entropy of e to the power lambda z divided by expected value e to the power lambda z. Remember that this is the divergence that we were looking for. This is that divergence q lambda f from p, and we are showing that this is less than equal to lambda square v by 2. So this by Herbst's argument, you just have to remember that formula for log moment generating function. It's the integral of this guy divided by lambda square. This is true for all lambda greater than 0. The log moment generating function of this random variable z. Yeah, so remember that you can always subtract expected value of z from both the exponents, because it's like multiplying with a constant. So this guy here is less than equal to lambda square v by 2. And this implies that this is a sub-Gaussian random variable, so we have a sub-Gaussian tail bound. Probability that a random variable z exceeds its expected value plus t is less than equal to e to the power t square by 2b. Okay. Alright, so this concludes the past few weeks of lectures, and so what we have achieved at the end of this is this very nice generalization of the McDiarmid inequality. And note that I have provided it as one-sided tail bound, the upper tail bound. If you want the lower tail bound, you have to apply this to minus z. If you apply this condition to minus z, this becomes z minus the soup over xi, soup over xi, that's the zi. And then you'll have the, if suppose that guy is bounded, then you'll have the lower tail bound. Okay. So, yeah, and in fact, if soup over xi minus inf over xi. If that thing itself is bounded, squared, if that thing itself is bounded, then you have both side tail bounds. Okay. That's roughly the part. Now, the main important thing here is this whole recipe. Okay, so we observed this very nice formula for we observed this very nice formula for the log moment generating function. That's where this entire thing started. So this particular formula, and then it follows that if we bound this quantity by a constant, then that gives us sub-Gaussian bound for the log moment generating function. And more importantly, perhaps bounding this quantity can be handled in a nice way, because this quantity tensorizes. Okay, this quantity in particular gets related to entropy, and that entropy tensorizes, and therefore, since entropy tensorizes, whenever we want to prove a bound for entropy, we can prove bound on this individual components separately. And we did prove one such bound using a variational formula for entropy, which we saw in the middle. And then we obtained this nice inequality, which is called the modified log-Sobolev inequality. And this function phi that we obtained in this application, we were only looking at one-sided tail bounds under this assumption, and therefore we could, for that direction, we use an approximation for this phi. Where is that approximation? Yeah, this guy here. And therefore this inequality gets you z minus zi square, lambda square. And then this tensorizes, so this gets bounded by lambda square v, and then you have bounded this ratio effectively. And then using the formula for log moment generating function, we get the sub-Gaussianity bound for the log moment generating function, which in turn implies the sub-Gaussian concentration bound, sub-Gaussian tail bounds. Okay, so this is the entropy method, and we have illustrated this using this binary log-Sobolev inequality, Gaussian log-Sobolev inequality, and now finally for general random variables. Okay, so this concludes our discussion of the entropy method. In the next lecture, Aditya will start with the transportation method, which is the second major approach for proving concentration bound that we'll see in this course. And just like this entire entropy method was based on this particular formula, as I've mentioned several times earlier, the transportation method will be based on this formula, the Gibbs variational formula. And there we will use the fact that this difference here can be controlled using a transportation inequality in terms of divergence, and that will yield another upper bound for the log moment generating function, leading to sub-Gaussian concentration bounds. So see you in the next lecture.